Hello, my name is Julius from Willich, and I will present to you Podoportation, foot-based locomotion in virtual reality. As many users of VR might know, there's a vast difference between the almost infinite virtual world virtual reality can present to the user and the actual physical world the user resides in. This can lead to the user bumping into their surroundings, which can be circumvented by systems such as the chaperone system, which displays a grid in front of the user should they come too close to fit their physical space's boundary. In applications, this can be prevented by using artificial locomotion techniques such as teleportation or button press to move, but those are usually initiated by pressing a button on a controller in the user's hands. However, humans use their hands for much more dexterous tasks or even for communication in social interaction. Furthermore, humans are even capable of using their hands while locomoting around the world. So walking and using your smartphone is not that difficult of a task for most persons. So approaches have been made to free up the user's hands in virtual reality by approaches such as head tilting or stepping in place to elicit locomotion, or by redirected walking, which alters the virtual world around the user to trick them into walking in circles while believing they are walking in a straight line, which can also be augmented by using electromuscle stimulation to force the user to walk in a tighter circle. Other approaches are walk in place, such as the Cyber Earth Virtualizer, which holds the user in place and tracks their feet movement to make them walk in the virtual world while using minimal space in the physical world. Our approach, Podoportation, uses the human's feet for teleportation inputs to allow the user to stay still in the physical world while still walking around in the virtual world and having their hands free. For this, we split up the teleport into its two main components, which is the distance and the direction of a teleport, which defines a clear target for the user. For distance, we define three input modalities, such as the toe lift, which might remind the user of hand-based teleportation, where you can control the distance of a teleport by lifting your foot to teleport further or putting it downward for a shorter teleport. The other input modality we used is foot distance. So we use the distance between the user's feet to control the distance of the teleport, albeit we exaggerate the teleportation as to have a further teleportation in the end. The third approach for distance we used is the weight distribution. So users lean forward to teleport further away and lean backward to teleport a shorter distance. The next component of a teleport is the direction. So for the direction, we also have three input modalities. One is spanning a vector with your 2 feet, which we just stretch out for to the final target with the distance modifier. The other is just pointing with your foot towards the direction that you want to teleport to. And the third is a mixture of the pointing from the input modality before, but you can make smaller adjustments by leaning left and right. So if you just slightly to the left or the right of your target, you can make small adjustments. This leaves us with a total of 3 input combinations if we combine all the input modalities with each other. And we wanted to evaluate them according to accuracy, efficiency, and convenience. For the accuracy, we used the error in meters to the desired target of the user. For efficiency, we used number of teleports and task completion time. And for convenience, we used another TLX and a custom questionnaire. The setup was as follows. The user was given a virtual space, which was marked red and green, so the user knew in which direction the targets they should teleport to would spawn to reduce search time. We had set distances in which the targets could spawn, and we spawned the targets at random in this area in front of the user, and only one target at a time. For input, we designed this hardware prototype. It had pressure sensors in the front and in the back, and a standard Vive tracker for positional tracking. Let's get to the results. So, concerning efficiency of the input modalities measured in task completion time, we found that the pressure in distance, the distance pressure modality was significantly worse than all the other modalities, and no significant differences between the rest. This compared to the point and teleport, which gives you an indication on how it holds up to established teleportation techniques. You can see point and teleport is still better. However, we did not introduce an artificial task which occupies the user's hands, which might have increased the task completion time for point and teleport, but we wanted to have a baseline that does not include an artificial task to not skew the results. For the number of teleports, we could find that the toe lift modality is significantly better, so has a significantly lower number of teleports compared to the pressure distribution input modality for distance, and no other significant difference between the input modalities. Now for accuracy, this is error in meters to the target. We found that for the distance modality, the toe lift and the foot distance modality was significantly better than the pressure modality, so less error. And for the direction, we also found that the point with 1 foot and the point with the vector of 2 feet was significantly better than the pointing with pressure adjustment. So again, smaller error, better result. For another task load index, we found that the distance modality, the toe lift and the distance again were significantly better than the pressure distribution. For the direction, however, only pointing with 1 foot was significantly better compared to the 2 other modalities. For the custom questionnaire, we asked for one for the convenience of the users with the input modality, and the other question was if they were confident that they arrived accurately at the target. For the convenience, we found that users found the pointing and toe lift most convenient for regular use. This could be explained by the user being used to this input modality from their hand-based inputs from a controller. The other question about the confidence if they arrived accurately. For the foot distance, it was every combination with all the direction input modalities. They were confident that the distance modality was that they arrived accurately at the target. And for the special combination of toe lift and foot vector, so you point into a direction with both of your feet, that they were confident that they arrived accurately at the target. Furthermore, in the questionnaire, we asked the users which input modality they would like to use in VR in the future. And here we had 3 input modalities that users really preferred. The one was pointing with both feet and lifting your toe, pointing with 1 foot and distance of your feet, and pointing with both feet and distance of your feet. This could be due to the fact that engaging your whole body in the motion made it more interesting for the users to teleport around in the virtual world. From this, we could form design guidelines, which read as follows. There's no golden bullet for teleporting with your feet, and you should only use your feet for teleportation if the benefit of having free hands is worth the trade-off, or if you think that tasks done with the hand will slow down your normal hand-based teleportation significantly. So we also have 2 situations to consider. One is, do you want convenient locomotion? In this case, you should rely on pointing and foot distance, or on pointing and toe lift. However, if you want an engaging, fun, entertaining experience for the users, you should rely on pointing with both of your feet and distance, because there you modify the whole input modality at once, with which the users really enjoyed during the testing. Limitations. We could see that users had trouble controlling the center of pressure of one foot, because they are more used to sensing their whole body's center of pressure, which would require pressure sensors in both feet. We saw that we have no clear indication on how much improvement the free hands would actually bring in a real task, since we used a clear baseline with no secondary task in our tests. And we also have no real-world task at hand, so the users knew exactly where they were going. They had no obstacles that they had to work around, so it's not comparable to a real-world application at this moment. So in conclusion, we have this handy flowchart. So if you really want to use foot-based interaction, you have to be sure that freeing up your hands is really worth the trade-off. If not, you should just rely on standard hand-based teleportation. But if you want to trade off for foot-based teleportation, the next question is, should it be convenient or should it be fun? For convenience, you should rely on pointing with one foot and either foot distance or toe lift for your input modality. And if it should be fun, you should rely on pointing with both feet and relying on foot distance for the distance input, because this engages the whole users, or both of the users' feet in the targeting process, and was generally perceived as more fun than the other approaches. And finally, I would like to invite you to check out our other tasks at CHI, virtual CHI that is.